Hello, Mr. Collier here, and today we're going to continue our discussion of dynamics by talking about Sir Isaac Newton and the law of inertia. So today is Newton's first law. A little background about Sir Isaac Newton. He was born in England on Christmas Day, 1642, although there's some disparity between the calendar they were using at the time and the calendar we use today, so it might have actually been January 4th. And he was born actually the same year that Galileo died, and at age 12 he was taken out of school to be a farmer and help his grandparents on their farm, so he had a somewhat untraditional education. And yet, in spite of that, by the time he was 30, he had made a lot of very famous and long-lasting contributions to science. By the time he was 30, he had formulated Newton's laws of motion, which we're studying now, but he had done so much more. He'd also discovered the universal law of gravitation, which relates the mass of objects to how much gravity they have. So you can actually use that to calculate how much gravity there is on Earth, or how much gravity there is on another planet, or how much gravity there is between two planets, or between a planet and its star. All sorts of calculations can be done with that universal law of gravitation. He also essentially invented calculus, although this is another one where there were some other people working on calculus around the same time. But basically, he had been working with algebra to describe the motions of objects and said, this isn't going to cut it. I need to come up with something new, and he essentially invented calculus, a math that we still use today. But wait, there's more. He also explained why the planets move the way they do, and explained the motion of tides and studied that. And he actually is also quite famous for laying the groundwork for the field of optics, so taking a prism and splitting white light into the different waves of the electromagnetic spectrum and noticing that there's different colors, and white light is made of all those colors. So he was one to give credit, though, and there was a lot of scientists that came before him whose work he was working with, adapting, and adding to. So while he absolutely contributed a ton to science, he was willing to give credit to those who helped him. All right, so let's start. Let's tackle law number one. Newton's first law says an object at rest will continue to stay at rest, or an object in motion will continue to travel at a constant speed in a straight line unless compelled to change by forces acting on it. It's a bit of a mouthful. The way I like to think about it is an object maintains its motion unless there's an unbalanced force. So objects will keep doing what they are doing unless there are unbalanced forces acting upon it. And we're going to study those unbalanced forces in much more detail as we continue. But for now, let's just talk about balanced forces and what that means to an object. So we often call Newton's first law the law of inertia, because inertia is the property of an object to remain in its current state of motion. And that's literally what we're describing here. Objects tend to keep doing what they are already doing. Now, law number one does not mean that an object at rest or an object in motion in a constant way have no forces acting on it. It simply means that those forces are balanced. So for example, a ball sitting on a table has gravity pulling the ball down, but it also then has the table holding it up. And so the net result is two forces of equal strength in opposite direction, just as we've learned with vectors in general. They're going to cancel each other out. They're going to result in a net force of zero and no motion. We call this equilibrium when forces are balanced out and an object has zero net force acting on it. It's also true for objects that are moving at a constant speed. Forces are balanced again. So when a skydiver is falling and reaches terminal velocity, they have gravity pulling them down, that's a force, but they also have air resistance pushing them up. These two forces are balanced. They will still move, they're still going to fall at terminal velocity, but they will no longer accelerate. So mathematically what we're saying here is that the sum, and that's what this symbol here means, the sum of all the forces is equal to zero. And when that's the case, the net force is zero. And there is no acceleration when the net force is zero. In other words, when the net force is zero, an object in motion stays in motion, an object at rest stays at rest. Of course, this then asks the question, what happens when the forces are not balanced? What happens when there is a net force acting on an object? And when that's the case, Newton has another answer for us, and that's going to be law number 2, which we're going to discuss in our next video.